In this video, I will teach you Clojure. We are going to use this interactive diagram with code snippets built in OrgPad, which is itself built in Clojure. And I think the main point is to start with the data. So there are basic data types you probably know from other languages. We have nil, which is null, we have booleans, we have numbers, we have strings. There are also these keywords I will get to a little bit later. There are symbols which refer something else. In this case, I'm getting a warning that ABC is undefined, but let's say I will set the value 42, and when the code is reloaded, you can see 42 is here in the output. And there are also regex and a few other stuff. And this data can be grouped into data structures. Clojure data structures are really amazing because, first of all, they're immutable. So they cannot be modified, and if you want to create a modified copy, you create a new copy on the side. But it actually is very efficient, so it is doing some sharing under the hood. And they also allow you to mix data types and arbitrarily nest inside each other, similar to languages like Python. There are 4 basic data structures. There are lists, which I'm not going to spend that much time about. They are basically just linked lists where you can quickly access or modify the first element, but getting to the end of the list is expensive. Then there are vectors, which are sort of like arrays, but immutable arrays, and you can quickly get to any index. Like for instance, here I'm getting the 3rd index. I can get the 4th index, the 5th index, and so on. If I get the 6th index, I get an error because there are only 6 elements in the list. Yeah, the indexes are going from 0. Yeah, I can modify the list by adding something to the end, etc. So these are vectors. Next are sets, which are written with hash and curly brackets, and these are basically they contain some elements, each exactly once, but the order is not important, and you can quickly check whether a given element is in the set or not. And last but not least are maps, hash maps, where you have basically pairs of key and values. So to each key you have some value assigned. So I have a map like this written in curly brackets, where the key and the values are basically the pairs. So you have even number of elements here, forming key, value, and so on. And you can quickly get to a value for any key. You can modify it. You can see that it's immutable. Say, for instance, if I add something here, I will create a new map containing the key D and the value another value, but the original map M is left in touch. So if I remove B, you can see here I don't have another value, and so on. So this is very powerful. So these are the data structures. Let's talk about the code. So if you want to call a function in Clojure, because it's a little bit unusual. Basically, instead of this normal form you know from all the other languages, you just place the parentheses in front of the function, and also commas are optional, so we usually leave them out. And there are very nice implications of that. So for instance, there is this built-in function max, which takes an arbitrary number of numbers, and it will compute the maximum for them. And it is nice that actually arithmetic operators are called normally as any other function, and they also take arbitrary number of arguments. Even 0 arguments is valid. And I can easily modify this stuff by nesting another arithmetic operator inside, like this. I get a different value. Yeah, there is, for instance, also built-in function count, which given a collection will compute the number of elements. And what is really important about this change here is that actually code in Clojure is just data. Consider this piece of code. So as a code, it is calling the count function on vector 1 up to 5. But as data, this is a list, you see the round bracket, then a symbol, and a vector. And vector contains 5 numbers. So basically what happens is that you code in the data structures you have seen before, and then the compiler will basically interpret these data structures and run them as code. So basically whenever you see lists, they actually correspond to calling a function. And usually we don't use lists as data structure much in the code, except when we work with the code itself. And one nice consequence of this, which I'm not going to talk about, are macros. It is really easy to build very powerful macros in Clojure. Macros are basically a piece of code which will be given a code as a data structure and will transform this data structure into another data structure, which is then run as a different code. And if you take any other language, for instance JavaScript or Python, and you think, okay, I'm giving this code snippet and I want to transform it into some other valid code, it is actually really tricky to do compared to macros in Clojure. Yeah, so this is how functions are called. If I want to define new symbols or maybe new functions, there is this built-in for def. So I have def, and then I have a symbol, and then I have the value for the symbol. And what happens is that the value 42 is binded to symbol value. So when I now call value, I will get 42 here. I can also define functions with this def and average. So def and form will take the symbol, which is the name of the function. There is the option, a documentation string. Then the arguments of the functions are written as a vector of symbols. And then I have the function body. And the last form, this thing here, is the return value of the function. So for instance, if I would want to write the maximum function, like my maximum, which will take two values and it will return you the larger one of them. So let's say if y is larger than x, I will return y, otherwise I will return x. So I can do it like this, and then I can say, okay, my maximum of 5 and 3, 5 and 7, and you can see that it works. So this is how you build functions in Clojure. Yeah, so it is also possible to quickly define anonymous functions, and actually functions are also values which can be passed to other functions and stored and worked with like that. So I can use this def malt fn. This is just basically the shorthand for defn you have seen before. So you don't have to write it like this, you can just basically save one pair of parentheses. And so I'm defining a new anonymous function which takes two values and multiplies them together. There is also this shorthand notation. If the function is really simple, you can use hash in front of the brackets, and then you use either the percent sign when the function takes a single argument, or you can use %1, %2, and so on if it contains multiple arguments, if it uses multiple arguments. So I have this multiplication function down here. You can see it returns me an object, CLJS user multiply. So you can see that it is really a function. I can call it, multiply 2 by 3, I get 6. I can multiply 2 times 8, and so on. And anonymous functions, of course, don't have to be stored inside a symbol. They can be called directly. So this is an example of an inline average function. It's like this. Okay, so let's take a look at some basic functions. Let's see the functions for numbers. So we have the usual arithmetic operators. So we have plus, we have minus. For a single argument, it will just negate the value. For multiple arguments, it will subtract the remaining ones from the first one. There is the multiplication, there is division. In Clojure script, which is what is running here, we get a float, but in Clojure you get an exact ratio. You have also integer division and the mod or the remainder. There are actually two different functions, mod and remainder, which behave a little bit differently for negative numbers. And you can see the documentation. There is also the inc and decrement function, which you probably know from other languages as the plus and minus operator. There is the maximum minimum function, and there are some useful built-in tests, like testing whether a number is even or odd, or whether it's zero, positive, negative. There is a convention in Clojure that functions ending with 0 return a boolean. So of course, you don't have to follow it, and using things like question mark or exclamation mark and so on is perfectly valid within symbol name, but it is a useful convention to follow. And okay, let's see a little bit more. So what about comparison and logic operators? So in Clojure, when testing whether some value is true or not, there is this concept of truthy. So truthy is every value which is not nil and false. So there are only two values which are basically false, and the remaining values, like for instance 0, is truthy. So if I have these two symbols x to value 10 and y is nil, then yeah, for instance here y is not truthy, so OR will pick me up the second value. It's really nice because OR can be used in other things. If it would return always true or false, I couldn't use it so easily. So in this case, I can use it, for instance, to set default values. So if y is basically not defined, it's nil, then I will use 5 instead of it. Yeah, and so you have the usual number comparators. In Clojure, they again take arbitrary number of arguments. So this is a quick test whether this sequence is increasing. So it is not, as you can see. Now I change it and it is increasing. This is a quick test whether x is between 5 and 15. It is much more understandable than to write and smaller or equal 5nx and smaller or equal x15. This is way more cluttered, way harder to follow. Yeah, so Clojure is really nice in making things compact and more understandable. There is the there is the equal comparator, which basically compares two things whether they are the same, and it works really well. And in certain situations, it does not distinguish between different types of data structures, so a vector and a list are equal, or sequences. And this is good because you don't have to care that much about the precise data type. It's just basically logic comparison that they contain the same elements. And there is not equal, so instead of cryptic symbols like not equal, like exclamation mark equal, you have just not equal. That's quite nice when you get used to it. Now there are the logic operators, or basically the symbols OR and AND. OR returns the first truthy value, or nil, and returns the first non-truthy value, or the last value, basically here. Yeah, if we have false, you can see that yeah, you get false. So OR returns the last non-truthy value. And there is the not, which will negate the result is always a boolean. And basically, normally having any truthy value is fine. You don't really care about boolean. But if, for instance, you want to pass it outside to Java or JavaScript, you can basically convert it into a boolean like this. Yeah. So this is really easy. Now I can use this for conditions and branching. So if I have this value x equal 5, I can write like if statement. If x is smaller than 5, I will print this. Otherwise, I will print the other part. So basically, it contains this form is used as then, and the other form is used as else. And if I go here and I change it like this, you can see that the output is changing. And there are a few other nice things. I mean, you can use if inside of anything, so it's much more useful than, for instance, in C or in Java, where the if statement has to be outside of everything. So it sort of works like this question mark double colon operator in C. And there is the when form, which is just basically then branch. There is no else branch. There is cont, which allows to have multiple branches. There is a case which does some compile time optimization, so it's a little bit faster if the values here are known during compilation, but not that important for now. Okay, so let's see. There is this thing I want to show. Here are the high order functions. High order functions basically are functions which take another function and take a collection and apply this function on the collection in some way and return you maybe a modified collection or some computed value. And they're basically used in all languages nowadays, but Clojure has their code incredibly clean and it's really fun to work in this way. So, for instance, suppose that I have this list of maps, each map corresponding to one person, and now I can play with map. So map is taking some function, for instance, increment here, and then a collection, say numbers from 0 to 9, and it will apply the increment function on each element of 0 to 9, so increment it by 1, and then will output the resulting collection. So the resulting collection is 1 up to 10. Each number is increased by 1. Since yeah, let's actually take a look at this keyword. What it is. So why we need keywords? And you can think of keywords as basically program-wide unique identifiers which identify themselves, sort of like enums in languages like C++ or Java, but they're application-wide, they can be serialized, they're easy to understand. Instead of using strings like in JSON, you can actually instead of using strings like in JSON, the keywords are faster because they're cached. Basically, there is a unique place in the code where all the keywords are stored, and if you want to compare to keywords, you are just comparing the addresses. So it's really fast, and yeah, it's also possible to distinguish them using namespace prefixes, so they can be unique within the entire application. And usually we use keywords as keys in maps because they're really useful. So for instance, here I have a keyword ABC. I can also have a keyword with myapp prefix, and they're different keywords. And I can also build them programmatically from strings. As you can see here, I get myapp ABC. Yeah, these two things are the same. Now I get true now. And I can also obtain these strings back from a keyword. And what happens usually is that you have some map like this. Say ABC is XYZ and DEF is 1, 2, 3. And now if I want to get the value of, say, ABC from it, I can use the get function like this. But also the map can be used as a function, but also a keyword works as a function. So I can swap the order and have it like this, and the keyword is a function which will take itself out of a map. So in this case it works like this. If I put some keyword which is not there, I will get nil. So I can play with keywords like that. And so what we are actually, so here you have maps and you can play with them, we can modify them. What really happens here is that we can represent objects. We can represent objects from the other languages. We usually just basically build them into maps. So here is an example. If you would be using some object-oriented language, you would create an user object, and then you would have an array of users. But here I'm just fine with representing each user as a map, where different fields are stored under these keywords. So there would be a name field. It is just stored as a keyword user/name. There will be age field, user/age, and so on. And I can nest the structures inside each other. So for skills, I have a set of skills of a person. You can see the usage of keywords as identifier within the application. So I can also use the same skills elsewhere, and I can easily search them using my ID and so on. And so I have this vector of users, and now I can apply these high order functions and basically use the standard logic to process all of these objects. So when you create an object in object-oriented language, you are going to end up with writing a lot of code which is specifically working only for this object. But if you represent your objects as data, as maps, you can use these nice general functions to process them, and it leads to a lot less code and less coupling and so on. So if you would be interested to learn more about this, you can take a look at this new book, which is about data-oriented programming. It is explained on JavaScript, so you don't even need to know Clojure, and it leads basically to greatly simplifying complexity and making the systems easier to change and so on. So this is really an amazing way how to work, and the entire org path you see right now is written using these techniques. Yeah. So if and another beautiful thing about the Clojure data structures are sequence abstractions. So basically all of these data structures can be processed using a unified sequence interface where you have a first value and then you have the rest of the values. So you can build unified algorithms on them. So if I have a map here and I try to seek it, process it, I will get a sequence of pairs of key and value, and so on. And then I can apply, for instance, map on it, like this. Say this is, I have a map here. If I will comment this, this out, I will get, after processing, I will increment the value by 1. So I get A is 3, B is 6, C is 9, D is 11. Yeah, then I will filter the values which are odd. Now you can see that only, so B is taken out, because B would be 6 after incrementing. And then I can build another map out of it again. So yeah, I can basically use these unified algorithms, and I don't really care whether my value is a map, or is a sequence, or is a vector, or is a list, or is a set. I get all of these algorithms working on all the data structure. And it even works on other things like array lists in Java, and you can easily extend any other data structure to implement the IC interface. So it's really amazing. And so I have this map function which works on all the sequences, on all the collections. And here is an example that it's amazing to use a keyword as a function. If I want to get a particular value out of a sequence of maps, I can just use the keyword, and it's really easy. Yeah, I can also do some modifications within the map, like increase age of each person. Yeah, and it's even possible to take multiple sequences. Range here is an infinite sequence going from 0 to like infinity. And it's lazy, it's never realized within the program. So only the values I need are actually computed. And so I put both of these sequences together, and then it allows me to basically add an index to a person. If I would want to, for instance, display it in a table, I would get an index like this. And there are other higher order functions. There is the filter remove, which will get a function. It will test the function for each element of the collection, and it will decide if the test is truthy, it will be kept, otherwise it will be removed. There is the reduce function, which is there is a mistake here actually. I will have to fix that. Yeah, I think that's sort of a quick introduction of Clojure. You can play with this diagram if you go to the link in the description, basically orgped.com/s/clojure-tutorial. And yeah, let me show you the one last thing here. So this is an example how we can generate HTML using data. We are using this awesome hiccup notation, which basically represents HTML using nested vectors. So each HTML tag, like B here, for instance, the bold text, is a vector where the first you have a keyword corresponding to the tag. Then you have the optional map for arguments. So like here there is the style text decoration line through. It's optional, it can be skipped out. And then you have the remaining elements of the vector are children. Yeah, and it's even possible to use the sequences that are just basically like flattened, like they're removed when rendering. And there are libraries which basically take this hiccup data format and will produce HTML out of it. Or for instance, here I'm running Reagent, which uses hiccup directly to render React components. So this stuff here is running React, and finish the video here. So if I add it, you can see that it is modified immediately. I can also, for instance, add it in the done list, and it will be good. And yeah, I can modify the code itself, and you can see it immediately reloads as well. So let's say let's add style font size is 15, 25. Now I can see I can play with that. What is it? 12. Yeah. I can play around this. So hiccup notation is really awesome, and in the end it is just a data structure, so you can use all the techniques you have seen in this video to play with the data structure and to modify it and add some stuff. Like here you can see that I'm using some data about the to-do lists, and I'm just basically building it here so it works as a templating language. When I work in Clojure, I don't need a separate templating language. I can write my CSS using Clojure, I can write my components using Clojure, and so on. You can rewrite configuration files as these documents in Clojure, and so on. So it's really universal and amazing. So this is the Clojure diagram. If you got interested by this, you can spend a little time playing here. Then it is really good to actually get working Clojure setup in your IDE with a repo, which allows you an amazing feedback loop. And if you're interested about this, I can make another video and talk about how to get started on your own computer. And if you would be interested in Clojure, to learn more about the ideas and philosophy, I have built this document which summarizes the language itself, and there is also this video how you can use OrgPad for all your IT needs. So thanks a lot for watching. Bye.